So in this section, we're performing addition and subtraction of rational expressions. And when we add or subtract rational expressions, or adding and subtracting of fractions, we could have like fractions or unlike fractions. Like fractions have the same denominator. So in this example I wrote here, we have 3x plus, rather 3 over 7 plus 11 over 7. So if we were to perform this operation, when I'm adding fractions and the denominators are the same, we keep the denominator. And then we perform the operation of the numerator. So in this case, it's addition. So we're going to add the numerators. 3 plus 11 is 14. And then we would reduce, and we'd get 2. So the same thing with rational expressions. Right, if we have a procedure, let's see what we did in this problem. Well, they were like fractions, so we keep the denominator. Keep the like denominator, has to be the same. Then we perform the operation on the numerators. So we add or subtract numerators. And then we simplify or reduce. So now you guys could do one. Let's see. 3x plus 2 over 3x plus 4 plus 3x plus 6 over 3x plus 4. So let's try this problem. I'll give you a second to look at it. So I'm going to keep my denominator, which is 3x plus 4, and I want to add my numerators. Let's write it as a single fraction. This is 3x plus 2 plus 3x plus 6. That's interesting. Hold on one sec. So our like terms are 3x and 3x. So I'm going to have 6x, and a positive 2 and a positive 6 gives me positive 8. So my numerator is 6x plus 8. My denominator is 3x plus 4. I kept the like denominator. I added the numerators, and now I have to simplify this. Now remember, to simplify a rational expression, you factor and cancel. Factor, then cancel. You can't cancel first. I'm sure a lot of you tried canceling here. Don't cancel. Factor out. In this case, I have a GCF here of 2. And here I have no GCF. So I factor. I find my like factors. I could cancel them out. So my final answer here is 2. Let's take a look at this example. It's a subtraction problem. They are rational expressions, and they're like because both of the denominators are the same. So we want to follow that same procedure. This one is a little trickier. Keep in mind that's a subtraction sign. So you got to remember, you got to subtract everything to the right. I'll give you a minute to write it down and start it, and then I'll start it. So if we follow the procedures I've prescribed, we'd have x squared minus x minus 6. We keep the denominator. And then I have up top, I want to subtract my numerators, x squared minus 4x minus x minus 6, but I'm subtracting both of these. So you might want to put that in parentheses. You're not only subtracting the x, but you're subtracting the negative 6. Subtraction of x and the subtraction of negative 6. That's the part that I said might be tricky. You have to remember to distribute your subtraction. You're subtracting all the values to the right. So this is really x squared minus 4x minus x plus 6 all over x squared minus x minus 6. I can combine my likes, so it looks like I'm going to have x squared minus 5x plus 6 all over x squared minus x minus 6. Now I could simplify. I could reduce this fraction. In order to reduce, we know we have to factor and cancel. Right? We can't reduce before we factor. So up top, it looks like I'm going to have x times x is x squared. And 2 times 3 is 6. And a negative and a negative. On the bottom, I have x and x. And 2 times 3 is 6. And a positive and a negative. Right? Positive 2 and a negative 3 give me my negative 6. And my inners and my outers give me my b term of negative 1. Once I factor, I could cancel out my like factors. And my final answer in this case looks like it's going to be x minus 2 over x plus 2. All right, so here's another subtraction example for you to try. I'll give you a minute to play with it, and then I'll come back and work on it with you. So I kept my denominator. I'm subtracting my numerators. It's the same as subtracting any polynomial. We distribute the negative. So I'm going to have a 2x plus 3 minus 3 plus x all over 3x minus 6. I can combine my like terms.
How do you know when to use the parentheses?
You could always use the parentheses because whether you're adding or subtracting, but it only have to distribute in the parentheses when it's subtraction. Right? If this was a plus sign, right? If this was a plus sign, I could still distribute a positive 1. It wouldn't change the answer.
Mm-hmm.
So you're probably better off being consistent and always putting everything in parentheses, right? I could put that one in parentheses also and say it has a 1 out here. And then I distribute it, and I get 2x plus 3. I put this one in parentheses. I have a 1 out here. I distribute the -1, and I get this. So just like with polynomials, adding and subtracting polynomials, you distribute what's on the outside of the parentheses.
Thank you.
Yep. I could cancel out my like terms, or rather I could combine my like terms. So I'm left with 3x over 3x minus 6. And in order to simplify this, we have to factor. We cannot cancel until we factor. This denominator could be factored. I'm running out of space. So I'm going to have 3x up top. And on the bottom, I could take out a 3. And I'm left with x minus 2. And now I could cancel out my like factors. Here I have 3 times x. Here I have 3 times x minus 2. So my 3's cancel out. My final answer is x over x minus 2. So we're moving forward with addition and subtraction of unlike fractions. Unlike fractions, the denominators differ. Different denominators, which you've done prior. I'm sure you've added and subtracted fractions before, and when they're unlike fractions, it's a much harder problem. Right, when we're adding and subtracting with unlike fractions, and the denominators are different, we have to find the LCD, which is a little bit of a pain in the neck. We have to find a value that both 8 goes into and 6 goes into. LCD stands for lowest common denominator. We could always find a common denominator, not necessarily the lowest, by just multiplying these two. 6 times 8 is 48. That would be a common denominator. But ideally, we'd like to find a smaller number, a number that both 6 and 8 could go into. We could count by 6s and count by 8s until we find a common denominator. Right? If I count by 6s and count by 8s, I know 6 times 4 is 24 and 8 times 3 is 24. So my LCD in this case is going to be 24. It has to be a value that both I see 8 could go into and 6 could go into. And then really what I'm doing is I'm saying, well, I want this 8 to be a 24. So what did I do to this 8? I multiplied it by 3. Whatever I do to the bottom, I have to do the same to the top to keep this fraction true. So this is going to be 12. And over here, the same thing. This 6 became a 24. How did it become a 24? Well, I multiplied it by 4. So 3 times 4 is also 12. So I find a LCD, then I multiply by the missing factor, the missing multiple. Right here, I multiplied, so that way I had my 24 on the bottom, my 12 up top. Now I can combine my like terms up top. Combine like terms in numerator. So I'm going to have 24 over 24, which this isn't the best example. And then I could reduce or simplify. If it was an algebraic fraction, we'd simplify by factoring and canceling. In this case, 24 divided by 24 is 1. Let's look at an algebraic fraction or rational expression. In this example, I have 2 over 3x minus 4 over 5x squared y. If I follow the same procedure, I want to first find an LCD. I want to find a value where I could see both the factors from this fraction and both fractions, and factors from this denominator as well. 3x has to be able to go into it, and 5x squared y has to be able to go into my LCD. So let's first look at the 3 and 5. What value can 3 and 5 go into? 15. Right? 3 goes into 15 and 5 goes into 15. So we took care of those. Now I have an x to the first power and an x to the second power. I want something that both of those could go into. X to the second power. Right? X to the second power goes into x to the second power, and x to the first power also goes into x to the second power. Right? Because x to the second power is x times x. So I could see that has that in there also. Some people might say x to the third. Well, x to the third would be a common denominator or would work, but it's not the lowest value that both of those could go into. The lowest value that both of those could go into would be x squared. And then we're also going to need this y. Because we have to be able to have a value that 5 goes into, x squared goes into, and y goes into. So I could see it as representation for all of these. And 3 goes into, and x goes into. Right? There's a 3x in here also. So that's how we choose the LCD. Now, I suggest you multiply by the missing factors. I suggest you look here, and you say, well, what's missing from here to here? How did this become this? Well, the only thing that's really missing here is the multiplication of 3. So I want to multiply the top by 3. So this will now be a 12 up top. What's missing from here to here? Well, I want this to look like this, so it has to be multiplied by 5. It's also missing an x and a y. Right, I have one x, so I need another x to get x squared. And it doesn't have a y here, so I need a y. So I have to multiply the top and the bottom by 5xy, which will give me 10xy minus 12 all over 15x squared y. It's not very pretty. We would combine our like terms if we could. There are no like terms. Then we would reduce by factoring. Well, the only way I could factor this, it looks like I have a GCF here of 2, which would leave me with 5xy minus 6 all over 15x squared y. But once I factor it, nothing cancels out. So I didn't really need to factor it. So you could leave your answer like this or like this, right? Because nothing cancels out in this case. So here's 3 more examples of addition and subtraction of rational expressions. I'm going to work these out. I'm not going to give you some time to do it because these are a little bit tricky, and I'd rather guide you through it, especially the first one. Once you get the first one, the rest will make more sense. So this first one, once again, we're looking to find an LCD. And an LCD is a value where I'm going to be able to see this denominator can go into it evenly, and this denominator could go into it evenly. So I'm definitely going to need an x, because I need that to go into it. And I'm going to need an x plus 3. Right? This value, x plus 3, is together. Different from the problem before when they were attached by multiplication. These are attached by addition. This is a binomial. So in this case, when we find our LCD, we need to see all the factors from here are represented and all the factors from here are represented. So it actually comes out a little bit easier once you find the LCD, because once again, we're just saying, well, what's missing from here to here? What does this denominator have that this one doesn't? X. So I have to multiply top and the bottom by X. And what's missing from this denominator to this denominator? Well, this one's missing X minus 3. So I have to multiply the numerator by X minus 3, or rather X plus 3. So I multiply by the missing factors. And now I could simplify my numerator. And then I'll reduce if I can. So to simplify the numerator, I'm going to distribute. So I have 4x plus 12 minus 3x all over x, x plus 3. I can combine my like terms, so it looks like I'm going to have 4x minus 3x is just x plus 12 all over x, x plus 3. Nothing factors, so I can't reduce it any further. It looks like the answer here is x plus 12 over x, x times 3.
Why is the first denominator x and then parentheses x plus 3? Why is it not just x plus 3? Because technically, wouldn't that work too? Or am I wrong?
No, it's an interesting question. So you're saying we could use x plus 3 as a denominator, but x doesn't go into this evenly, right? If I have x plus 3, that's not divisible by x. Right? I can't cancel these out. Do you agree?
Oh, okay, yes, because it has to be able to cross itself out.
Right? If this problem was 4x minus 3 over 3x, or make this a 5 over 3x or something like that, well, now my LCD could be 3x. Because x goes into it, right? 3x is divisible by x, and 3x is divisible by 3x. That came off the page here. Right? It's attached by multiplication is different. Right? This isn't divisible.
Got it. Thank you.
And if you think about it as a value, because this trips a lot of people up, think of x as a value. Right? If x was 5 plus 3 is 8. Right? That would give me 8/5. That doesn't reduce. Right? That's why nothing could cancel here. There's not a like factor here. But if x was 5 here, I would have 15 over 5, and that does reduce. It has a common factor. Factors are attached by multiplication. So this addition is what throws it off. I might have over-explained that. But
No, that was helpful. Thank you.
you can't cancel out when it's attached by addition or subtraction, which means also as LCDs, addition and subtraction of a value does not create a factor. Factors are attached by multiplication. I'm going to stop talking. So in this example, my LCD, I need this entire denominator expressed in my LCD, and I need this entire denominator expressed in my LCD. So my LCD is going to be x minus 2, x minus 3. So what I'm really doing here is I want to see what's missing from here to here, which is x minus 2. So I multiply top by x minus 2. And the same thing here. What's missing from here to here is the x minus 3 and the x minus 3. Really what this is doing is this is making a like fraction. Right now my denominators are the same up here. So it creates a like fraction. So I have 8 times x minus 3 plus 2 times x minus 2. And now I could distribute and combine. My numerators. So I'm going to have 8x minus 24 plus 2x minus 4. I'm going to run out of room. I'll put it next to it. This looks like 10x minus 28 over x minus 2, x minus 3. And I don't think anything cancels. It looks like I could take out a 2, which would leave me with 5x minus 14 over x minus 2, x minus 3. My red pen just died. But nothing cancels. So you could leave that as an answer, or that as an answer. We're running low on time, so let's make this the last problem, or last example. This problem is a little bit different than the ones prior, and it'll add a step to our procedure because we want to find the LCD. But before we find the LCD, our denominators have to be in simplest form. They have to be in reduced form. We have to be able to see the factors in order to make a lowest common denominator. We need to see all the factors that are contained. So here we're going to have to factor the denominators first. Factor denominators, that scribble says. Why didn't we factor denominators earlier? Well, we should have if we could have, but in none of these problems, the denominators were factorable. If the denominators are factorable, we factor the denominators first, then we find LCD, then we multiply by missing whatever, and then we simplify the numerator, and then we reduce. So we added a step to the procedure right up front, and it's factoring denominators. So in this case, I'm going to take out 2. So I'm going to have x plus 4, that 10 died too. X plus 4. And here I'm going to take out a 3, and that leaves me with x plus 4. This is a good example. Because now I'm looking for an LCD, so I'm looking for representation from each one of these. So let's look at these coefficients out front, this 2 and this 3. I need a 6, because 2 and 3 could go into 6. They're attached by multiplication here to this x plus 4. So x plus 4 is something I'm going to need. And now when I look, if I look at just this denominator, I could see 2 goes into it, and x plus 4 goes into it. I could see this entire denominator could go into my LCD. Similarly, 3 goes in, and x plus 4 goes in. I could see that this denominator can go into my LCD evenly. I have all the factors from here and there, and I have all the factors from here and there. So in this case, all I have to do is multiply the numerator and denominator. I have a different pen here. I need this one multiplied by a 2 in order to get the 6. And I have to multiply this one by a 3. This was originally 2. Right? And then I would have like denominators. This would give me 6x plus 4, and this would give me 6x plus 4. That's my LCD. So up top, I'm going to have 15 plus 10. Oh, I'm sorry. I messed up. That's a 7. So I'm going to have 15 plus 14, which will give me 29 over 6x plus 4. At this point, I would factor and cancel if I could, but I can't, so I don't. So my final answer is 29 over 6x plus 4. Horrible, horrible stuff. I agree. I'd like to end it there, but I just want to show you something quickly. Because in pre-calc or algebra and trig and other classes, when it gets hard, sometimes there's shortcuts. And I think I explained this to you once before. If I had 2/3 plus 1/7, I have 2/3 plus 1/7. These are unlike fractions. The shortcut method that I use to add or subtract unlike fractions is I just multiply the denominators, which give me 21, and then I cross multiply from the bottom up. 7 times 2 is 14, 3 times 1 is 3, and then I perform the operation 17/21. I multiply my denominators, and then I cross multiply. It's an easy way to add or subtract fractions. So I could almost subtract these in my head, right? I know the denominator is going to be 18, and then I have 2 times 8 is 16. 16 minus 9 is, of course, 7. 7/18. 16 minus 9. My point of showing you this is because in even in this class, x plus 3 minus 1 over x minus 2, if you have a problem like that, you could use the same procedure. You can multiply the denominators and then cross multiply from the bottom up. So I'm going to have 5x minus 2 minus 1, x plus 3. And then from there, simplify. Minus 3. I'm only showing you this so you don't get discouraged, because like I said, when you go on to higher math, when you have sine of theta over cosine theta plus sine theta over sine theta, sometimes you're going to have to add fractions with trigonometric functions. And sometimes it's easier not to do all that work, but you multiply across. This would be cosine times sine. And then you multiply this way. Sine times sine is sine squared. And cosine times sine is just cosine times sine. We do that in pre-calc. And when we do it in pre-calc, I don't do all this LCD stuff. I multiply my denominators and I cross multiply. So don't get too lost in the algebra of this. This isn't easy. Adding and subtracting unlike fractions or rational expressions, I think, is one of the hardest topics in algebra. So practice it, but don't get discouraged.